Space is vast. It's filled with stars, planets, and galaxies, but it also holds mysteries. One of the most captivating is the black hole. Imagine a place where gravity is king, so strong that nothing, not even light, can escape. That's a black hole. For centuries, these cosmic objects were just a mathematical curiosity. Einstein's theory of relativity predicted their existence. Now, powerful telescopes and observatories are unveiling their secrets. Black holes aren't just theoretical constructs anymore. They are real objects with a profound impact on the universe. Black holes challenge our understanding of physics. They push the boundaries of what we thought possible. Studying them helps us unravel the very fabric of the cosmos. This journey will take us through the heart of a black hole. We will explore its formation, its properties, and its effects on the universe around it. Let's begin our Cosmic Odyssey. Stars are the cosmic furnaces where elements are forged, but even stars have a lifespan. What happens when a star runs out of fuel? The answer depends on its mass. Smaller stars, like our Sun, fade into white dwarfs. Massive stars, however, meet a more dramatic fate. They collapse under their own gravity, creating a black hole. Imagine a star much larger than our Sun. It's burning brightly, fusing hydrogen into helium in its core. As the star ages, its fuel dwindles. The outward pressure from nuclear fusion weakens. Gravity, always present, takes over. The core collapses in on itself with incredible force. This triggers a supernova, a spectacular explosion that outshines entire galaxies. The outer layers of the star are blasted into space. The core, however, continues to collapse. It shrinks until it becomes infinitely dense, forming a black hole. Black holes are defined by two main parts, the event horizon and the singularity. Imagine the event horizon as a point of no return. Cross it and there's no coming back. Not even light can escape its grasp. The event horizon is not a physical boundary. It's a region in space-time where gravity is so intense that escape becomes impossible. Think of it as a waterfall. Once you go over the edge, there's no swimming back upstream. At the very center of a black hole lies the singularity. This is where all the matter that fell into the black hole is concentrated. It's a point of infinite density and zero volume. Our current understanding of physics breaks down at the singularity. We don't know what happens there. Black holes are not just cosmic vacuum cleaners sucking up everything in sight. They actually play a crucial role in the evolution of galaxies. Their immense gravity warps the fabric of space-time, creating a cosmic dance. Imagine a bowling ball placed on a trampoline. The ball represents a black hole and the trampoline represents space-time. The ball's weight causes the trampoline to sag, distorting the space around it. This is how black holes affect space-time. This distortion affects the orbits of stars and gas clouds. Black holes can pull in matter, creating accretion disks that glow brightly. They can also launch jets of energy into space, influencing the formation of stars and galaxies. Black holes are not just destroyers, but sculptors of the cosmos. We often picture stars as eternal beacons, shining brightly for eternity, but even stars have a life cycle. They are born, they live, and they die. And their deaths can be just as spectacular as their lives. Massive stars go out with a bang, leaving behind black holes. In the 1930s, a brilliant young astrophysicist named Subramanian Chandrasekhar was pondering the fate of stars. He knew that smaller stars, like our Sun, eventually run out of fuel and cool down, transitioning into white dwarfs. These stellar remnants, though incredibly dense, are supported by a quantum mechanical phenomenon known as electron degeneracy pressure, and which prevents further collapse. However, Chandrasekhar realized that there was a limit to how massive a star could be and still end its life as a white dwarf. This limit, now known as the Chandrasekhar limit, is about 1.4 times the mass of our Sun. Stars below this limit can find a semblance of peace as white dwarfs, their story coming to a relatively quiet end. But what about stars more massive than this critical threshold? What fate awaits those that exceed the Chandrasekhar limit? For these stellar behemoths, gravity's pull proves too strong for even the exotic physics of white dwarfs to resist. They are destined for a far more dramatic and violent end. When a massive star exhausts its nuclear fuel, gravity takes over. The core collapses inward with unimaginable force. This leads to a cataclysmic supernova. Imagine a star collapsing in hours. The core reaches unimaginable densities and temperatures. Shock waves propagate outward. They heat the outer layers to billions of degrees. The supernova is one of the most luminous events. It can outshine its entire host galaxy. The explosion scatters heavy elements, seeding future stars and planets. Beyond the veil journey to a black hole. While the supernova marks the spectacular death throes of a massive star, it is not the end of the story. In fact, it is merely the beginning of a new chapter, one that leads to the formation of one of the most mysterious and awe-inspiring objects in the universe, a black hole. As the outer layers of the star are blasted into space during the supernova, the core continues its relentless collapse. If the core's mass exceeds the Chandrasekhar limit by a significant margin, no known force in the universe can halt its inevitable fate. Gravity reigns supreme, crushing the core down further and further. Imagine a point in space where all the mass of the star's core, once spanning millions of kilometers, is compressed into an infinitesimally small region. As the core collapses beyond a certain point, its gravity becomes so intense that it warps the fabric of space-time itself, creating a region from which nothing, not even light, can escape. This region, shrouded in darkness and mystery, marks the point of no return, the event horizon of a black hole. The black hole recipe: ingredients for a cosmic monster. The recipe for a black hole is surprisingly simple. Take a massive star, at least several times the mass of our Sun, and let it live out its life. As the star exhausts its nuclear fuel, gravity takes over, leading to a catastrophic collapse and a brilliant supernova explosion. If the remaining core is massive enough, gravity's relentless pull will continue to crush it down until it becomes a black hole. But black holes are more than just collapsed stars. They are cosmic enigmas that challenge our understanding of physics and reality itself. They are regions where gravity is so strong that it distorts the fabric of space and time, creating a singularity, a point of infinite density and zero volume at their very core. These gravitational behemoths lurk in the hearts of galaxies, influencing the motions of stars and gas across vast distances. They warp the fabric of space-time, creating gravitational waves that ripple outward like cosmic tsunamis. Black holes are both destroyers and creators, shaping the evolution of galaxies and the very structure of the universe itself. The point of no return, approaching the event horizon. Imagine yourself as a space traveler venturing closer to a black hole. You'd notice something peculiar about the blackness ahead. It wouldn't just be an absence of light. This blackness would have a distinct edge, a boundary in space. This boundary is called the event horizon. It's not a physical barrier, it's a region where gravity is so intense that the escape velocity exceeds the speed of light. Nothing can escape from within the event horizon. Section 2. Trapped by gravity's grip inside the event horizon. Now, imagine you've crossed the event horizon. What would you experience? Surprisingly, you wouldn't feel any immediate change as you pass through this invisible boundary. There would be no great wall of fire, no sudden shift in the fabric of reality. From your perspective, the journey inward would continue as if the event horizon didn't exist. However, your fate would be sealed. Once inside the event horizon, you would be inexorably drawn towards the black hole's singularity, a point of infinite density at its center. No matter how powerful your engines, no matter what maneuvers you attempted, you could not escape the black hole's gravitational grip. The fabric of space-time itself would be distorted in such a way that all paths would lead inward. Think of it like being caught in a powerful whirlpool. Once you're inside the whirlpool's current, no amount of swimming can prevent you from being dragged towards its center. Similarly, inside the event horizon, the flow of space-time itself would carry you towards the singularity, regardless of your attempts to resist. Section 3. Singularity, the heart of darkness. At the heart of a black hole lies the singularity, a point of infinite density and zero volume. Here, our understanding of physics breaks down. The laws of nature cease to apply. Gravity is infinitely strong, and space-time is infinitely curved. All matter is compressed into a single point. This creates a gravitational pull that warps space-time. Time stands still at the singularity. The singularity is a point of mystery. Some theories suggest it might be a gateway to other universes. Others propose it could be the end of space-time. Without a theory of quantum gravity, the true nature of the singularity remains unsolved. Section 4. Black holes, more than just empty space. It's easy to think of black holes as giant cosmic vacuum cleaners, sucking up everything in their path. But black holes are far more dynamic and influential than their name might suggest. They're not just empty voids in space, they are active participants in the cosmic dance of matter and energy. Black holes have mass, just like stars and planets. This mass warps the fabric of space-time around them, creating a gravitational pull that affects the orbits of nearby stars and gas clouds. In fact, astronomers believe that supermassive black holes, millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. These gravitational behemoths act as cosmic anchors, influencing the motions of stars and gas across vast distances. They can drive the formation of stars and galaxies, and they can even launch powerful jets of energy into intergalactic space. Black holes are not just passive sinks of matter. They are dynamic engines that shape the evolution of the universe itself. Section 5. Cosmic lighthouses, accretion disks and quasars. While black holes themselves are invisible, their presence can be revealed by their effects on the surrounding matter. As gas and dust spiral inward towards a black hole, they form a swirling disk of material called an accretion disk. This disk, heated by friction and intense gravitational forces, can glow brightly across the electromagnetic spectrum from radio waves to X-rays. In some cases, the accretion disk around a supermassive black hole can outshine all the stars in its host galaxy, creating an incredibly luminous object known as a quasar. Quasars are among the most distant and energetic objects in the observable universe, powered by the infall of matter onto supermassive black holes billions of light-years away. These cosmic lighthouses provide astronomers with a glimpse into the early universe, allowing them to study the conditions that prevailed billions of years ago. By observing quasars and other active galactic nuclei, astronomers can learn about the growth and evolution of supermassive black holes, as well as the role they play in shaping the large-scale structure of the universe. Section 1. A cosmic zoo. Unveiling the diversity of black holes. Black holes come in various types: stellar mass, supermassive, and intermediate mass. Stellar mass black holes form from collapsing stars, while supermassive ones anchor galaxies. Intermediate mass black holes are the elusive middle ground, crucial to understanding black hole evolution. Section 2. Stellar mass. Black holes, remnants of cosmic cataclysms. Stellar mass black holes form from the collapse of massive stars. When a star exhausts its nuclear fuel, its core collapses, triggering a supernova. If the core is massive enough, it becomes a black hole. Imagine a star 10 times the mass of our Sun collapsing into a black hole. The core's collapse reaches unimaginable densities, forming a neutron star or a black hole. If the core is massive enough, it becomes a black hole, a region where gravity is so strong that nothing can escape. Section 3. Supermassive black holes, guardians of the galactic center. Supermassive black holes, millions or billions of times the mass of our Sun, reside at galaxy centers. They influence the orbits of stars and gas clouds, acting as gravitational anchors. These black holes can drive powerful jets of energy, affecting galaxy evolution. Section 4. Intermediate mass black holes, bridging the gap. Intermediate mass black holes with masses between stellar mass and supermassive black holes are a missing link. They might form through mergers of stellar mass black holes or gas cloud collapses. Detecting them could provide insights into black hole growth and galaxy evolution. Section 5. The quest for primordial black holes, echoes of the Big Bang. Primordial black holes might have formed in the early universe just after the Big Bang. Fluctuations in the early universe's density could have created these black holes. Detecting them would offer clues about the universe's infancy. A one-way ticket to the unknown. What happens when you fall into a black hole? Imagine you're an explorer approaching a black hole filled with excitement and trepidation. Crossing the event horizon is a one-way journey, a point of no return. You prepare for the plunge into the abyss, eager to witness the ultimate fate of matter and energy. Spaghettification, the ultimate stretch. As you approach the black hole, the gravitational pull on your feet is stronger than on your head. This tidal force stretches your body like cosmic spaghetti. The stretching intensifies as you get closer, tearing your body apart at the atomic level. Spaghettification is a gruesome process, stretching you into a stream of subatomic particles. Time dilation, a black hole's time-warping power. Gravity warps both space and time, slowing time near a black hole. To an observer, you'd appear to slow down as you approach the event horizon. Your clock would seem to stop at the event horizon. From your perspective, time flows normally, but your friend's clock speeds up. This time dilation is a mind-bending effect of black holes. And black holes were once thought to be ultimate cosmic sinks, but Stephen Hawking proposed they might emit radiation. Hawking radiation suggests black holes slowly lose mass over time. Virtual particles near the event horizon can result in one particle escaping, carrying away energy. This challenges the view of black holes as completely black. Hawking radiation raises the information paradox. Quantum mechanics states information cannot be destroyed, but black hole evaporation challenges this. Does information disappear forever, or is it preserved in Hawking radiation? This paradox remains one of the biggest mysteries in theoretical physics. Black holes shape the evolution of stars, galaxies, and space-time. Their gravity molds the cosmic tapestry, influencing star formation and galaxy evolution. They create glowing accretion disks and launch powerful jets of energy. Black holes are both destroyers and creators, shaping the universe. Gravitational waves, predicted by Einstein, are ripples in space-time from massive objects. These waves carry information about violent cosmic events like black hole collisions. Imagine space-time as a pond, with gravitational waves as ripples from a pebble. Black hole mergers create strong gravitational waves, detectable on Earth. These waves provide a new window into the universe. Supermassive black holes at galaxy centers influence star and gas cloud orbits. They act as gravitational anchors, regulating star formation. Accretion disks around them can outshine entire galaxies. These black holes shape galaxy evolution through their immense energy. When a star wanders too close to a supermassive black hole, a tidal disruption event occurs. The star is stretched and torn apart by the black hole's tidal forces. The material forms a temporary accretion disk, releasing a burst of radiation. This cosmic death cry is visible across the universe. Black holes, with their insatiable appetites and enigmatic nature, have long been associated with the ultimate fate of the universe. As they continue to grow, consuming matter and merging with each other, will they eventually consume everything, leaving behind a cold, dark, and empty void? Imagine the universe in its twilight years, its stars long extinguished, its galaxies dark and desolate. Black holes, the last remaining denizens of this cosmic graveyard, continue their cosmic dance and their gravitational pull, drawing them closer and closer together. As they spiral towards each other, they release gravitational waves, ripples in the fabric of space-time that carry away energy, accelerating their final embrace. Eventually, they merge in a cataclysmic event, a cosmic crescendo marking the end of an era. But even black holes are not immune to the passage of time. Through Hawking radiation, they slowly evaporate, their energy returning to the universe they once consumed. The fate of the universe remains an open question, a cosmic mystery, yet to be fully unraveled. Black holes, those enigmatic cosmic objects where gravity reigns supreme, have journeyed from the realm of theoretical speculation to become tangible entities, their presence confirmed through observational evidence and their influence felt across the vast expanse of the cosmos. We've peered into the heart of these gravitational behemoths, exploring their formation, their structure, and the mind-bending effects they have on space, time, and the very fabric of reality. Imagine standing on the precipice of the unknown, gazing into a cosmic abyss that challenges our understanding of the universe and beckons us to unravel its secrets. Black holes, with their event horizons, singularities, and gravitational mastery, represent the ultimate frontier of human curiosity. A realm where the known laws of physics are pushed to their limits and where the very nature of reality is called into question. From the stellar mass black holes born from the explosive deaths of massive stars to the supermassive black holes lurking at the hearts of galaxies, shaping the destinies of stars and gas clouds across vast distances, these gravitational wonders continue to captivate our imaginations and inspire us to explore the universe's grandest mysteries. The study of black holes has revolutionized our understanding of gravity, space, and time. Observations of black holes confirm Einstein's theory of general relativity with remarkable accuracy. Black holes serve as cosmic Rosetta Stones, revealing the universe's secrets. Studying stars orbiting supermassive black holes measures their masses precisely. Gravitational waves from black hole collisions open a new window into the universe. Black holes, those enigmatic cosmic objects that once seemed like mere theoretical constructs, have emerged as powerful tools for probing the early universe, offering tantalizing glimpses into the conditions that prevailed just moments after the Big Bang. The study of primordial black holes, hypothesized to have formed from density fluctuations in the early universe, could provide invaluable insights into the processes that shaped the universe's large-scale structure and the distribution of matter and energy. Imagine traveling back in time, witnessing the birth of the universe in a fiery explosion of energy and matter. Primordial black holes, if they exist, would be like cosmic fossils from this epoch, preserving information about the universe's infancy and the conditions that led to the formation of stars, galaxies, and ultimately ourselves. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, have provided astronomers with a snapshot of the universe as it was just 380,000 years old. By searching for subtle variations in this radiation, astronomers hope to find evidence of primordial black holes, their gravitational influence leaving an imprint on the universe's earliest light. As we stand on the cusp of a new era of astronomical discovery, black holes continue to beckon us with their mysteries, promising to unveil even more secrets about the universe and our place within it. With the advent of new and more powerful telescopes, both on Earth and in space, astronomers are poised to make groundbreaking observations that will further illuminate the nature of these gravitational wonders. Imagine a future where we can observe the event horizons of black holes directly, testing the limits of Einstein's theory of general relativity and searching for deviations that might point to new physics beyond our current understanding. Imagine detecting gravitational waves from the mergers of supermassive black holes, witnessing the cosmic dances of these gravitational giants across billions of light years. And imagine unraveling the information paradox, understanding how information is encoded and preserved within black holes, potentially revolutionizing our understanding of the relationship between gravity, quantum mechanics, and the nature of reality itself. The future of black hole astronomy is bright, promising a deeper understanding of the universe and our place within it. Our journey into the heart of black holes has been a thrilling exploration of the universe's most extreme environments and the fundamental laws that govern them. We've encountered mind-bending concepts like spaghettification, time dilation, and Hawking radiation, pushing the boundaries of our understanding and sparking our curiosity to delve deeper into the cosmos's mysteries. Imagine yourself as a cosmic explorer, venturing into the unknown with a sense of wonder and a thirst for knowledge. The universe is our laboratory, and black holes are among its most intriguing subjects. Their study has already yielded profound insights, and the discoveries yet to come promise to be even more astounding. As we continue to explore the cosmos, black holes will undoubtedly remain at the forefront of our investigations, their enigmatic nature challenging us to expand our knowledge and refine our understanding of the universe we inhabit. Our Cosmic Odyssey continues, driven by an insatiable desire to unravel the universe's secrets and comprehend our place within its grand tapestry.